Welcome all. So today we will continue with our buckling chapter. In this chapter we have seen the static buckling, we have seen the dynamic buckling, then we derived the equations to evaluate the buckling loads in case of static buckling. In case of dynamic buckling we understood how to calculate the effect of the dynamic load and the buckling behavior. After that we delved into the finite element method. We looked how to model the systems in the finite element software. We took help of software named LS-DYNA, which is a conventional finite element software, and we modeled two systems in the LS-DYNA, and we saw the effect of the buckling. So today we will try to do some examples here. So today we will be dealing with some of the examples. So first example deals with the effect of load eccentricity on the buckling. So in this problem, a bar with the same properties as above is loaded axially, but with a small eccentricity. So there is a bar, and there is an eccentricity in the bar. It is loaded axially. The eccentricity is been given by E. The initial deflection due to this eccentricity can be approximated by this particular equation. So this particular equation has been used to model the deflection, the deflection function caused due to this eccentricity. So in this particular problem, it is being asked to compute the fundamental Fourier coefficient for the initial deflection. Then it is asked to see the effect of the eccentricity. To see the effect of the eccentricity on the Southwell plot. This plot we have done earlier also, and the estimation of the critical load. And after that there is a discussion of why it may be difficult to separate the effects of eccentricity and the initial shape imperfection in the experimental measurements. So basically it is being asked that when we do an experiment, why it becomes difficult to separate out the effect of the eccentricity and the initial shape imperfection. Remember when we were dealing with the shape imperfections and the eccentricity, at that point of time we tried to combine it in the linear equation. So what we did was we did a combined imperfection estimate. So we combined the effect of the eccentricity and the initial shape imperfection. So this thing we combined and used it as a Fourier series. So we dealt with the initial shape imperfection, and the deflection expansion. So initial shape imperfection we modeled by a Fourier sine series approximations, and we calculated the coefficient. And this is the differential equation. After that we put into the differential equations. And after that we got the particular and the general solution. And then we evaluated the behavior of the buckling. So after that we did a Southwell plot. So this is being again asked in this particular question. And using the Southwell plot we can determine the coefficients. After that we looked into the effect of the load eccentricity on the buckling. We modeled the buckling by this equation, and this was the coefficient corresponding to the eccentricity. And in this case the eccentric load shift the Southwell plot to a non-positive value. In the first case it was having a negative value, and in the second case due to the effect of the load eccentricity it is shifting it towards the right. So it is having a non-zero positive value. We evaluated the effect of the load eccentricity, and we did an empirical approximation to get the value of the eccentricity. So we denoted this thing using the core radius of the cross section. Imperfection also depends upon the column length. So as per the length equation we tried to approximate an equation to estimate the imperfections. After that we combined both the effects, both the effects of due to eccentricity as well as the initial shape functions in one combined equation. So this is how we dealt with the things out here. So now we are going to do one example, dealing with these things. So in this example the effect of the load eccentricity is being analyzed. Okay. So, the initial deflection due to this eccentricity is modeled by this equation, same as before. We are asked to compute the fundamental Fourier coefficient for the initial deflection and the influence of this thing on the Southwell plot, and then give our views on how it is difficult, why it is difficult to separate out the effect of the eccentricity and the initial shape imperfections, okay, when we conduct an experiment. Okay. So, this is the given problem. Okay. So, we start the solution. So, we compute the fundamental Fourier coefficient for the initial deflection. So, the initial deflection we are expressing as the Fourier sine series. Okay. So, the initial deflection is expressed in terms of a Fourier sine series. The Fourier coefficient is being calculated by this particular equation, okay, for a fundamental mode, okay, where n equals to 1. Okay. We calculate the value of a1. Okay. So, when we calculate the integral, okay, and substituting the standard functions here, okay, the first integral forms out to be this particular number. Okay. So, what we did was we started with the initial deflection equation. Okay. So, the initial deflection has been approximated by a Fourier sine series. Okay. This is the Fourier sine series. Okay. After that, the Fourier coefficient is been given by this equation. Okay. So, we evaluated it for the fundamental mode, we calculated the integral, okay, and this gives this particular value, twice L over pi. So, second integral, okay. So, what we are trying to do is that we are doing this integral, okay, this is the required integral, okay, and we are doing this integral by parts, okay. So, the second integral by parts again give this solutions, okay. So, after that we calculate each term, okay. So, therefore, the total I, okay, comes out to be L over pi, okay. So, this was the I term, okay. So, it is L over pi, okay. So, substituting back into A1, okay, twice E over L times L over pi, okay. So, the value of is twice E over pi, okay. So, the value of A1 is twice E over pi, okay. So, this is the solution for the first part. Compute the fundamental Fourier coefficient for the initial deflection. So, the Fourier deflection for the initial deflection is given by this term twice E over pi, twice E over pi, okay, where E is the eccentricity in the system, okay. So, the first part is being solved, okay. Second part, the second part deals with how does the eccentricity influence the Southwell plot and estimation of the critical load, okay. What is the effect of this eccentricity on the estimation on the Southwell plot as well as the estimation of the critical load, okay. So, we will look into this thing. So, the Southwell plot is a graph of deflection delta versus delta over P, okay, and it is used to estimate the Euler buckling load PCR, okay. When there is a load eccentricity E, the bar behaves as if it has an initial imperfection, okay. So, this can be approximated by an initial imperfection case also, and as we have seen earlier, we can combine both the effects due to the initial imperfections and the due to the eccentricity in a single formulation, okay. So, we can mimic this behavior as the initial imperfection also. So, what it will do is that it will increase the deflection even at lower loads, okay. Since there is an initial deflection already present due to the eccentricity, the deflection even at lower loads is more, okay. So, what it will do is that it will cause the Southwell plot to intercept above 0 on the delta axis, okay. Okay. So, we will go back to the Southwell plot. So, this is our Southwell plot, okay. So, this is a plot between delta and versus delta divided by P, okay. So, due to the lowering of this threshold value, okay, there will be an intercept out here, okay. So, as we can see, even at a lower values, okay, even at a lower values, okay, there the deflection will try to start, okay. So, we will use this property, okay. The intercept value in the Southwell plot corresponds approximately to the eccentricity E, shifting the linear plot upward. Okay. The slope of the southwell plot still yields the critical load. Okay. The slope is giving me the critical load, okay, but the intercept complicates direct interpretation. Okay. Since there is an intercept out here, okay, the interpretation is not straightforward. Okay. So, the eccentricity effectively increases apparent initial deflection, okay, since there is an eccentricity, okay, in the given system. Okay. So, the system is applied and there is a eccentricity in the system. So, there will be an initial deflection. Okay. So, if we look into the other way, we can assume this thing that the eccentricity has, what it has done is that it has increased the apparent initial deflection, okay, and it reduces the measured critical load if not accounted for. Okay. So, there will be a reduction in the critical load. Okay. So, this is the interpretation, this is the effect of the eccentricity on the southwell plot. Okay. So, the eccentricity, okay, it increases the apparent initial deflection and it reduces the measured critical load. Okay. The third part of the question, why it may be difficult to separate the effect of the eccentricity and initial shape imperfection in the experimental measures. Okay. In the experimental measures, why we are not able to sort these two things out properly, okay, or why we feel difficulty in doing so. Okay. What are the challenges out here? So, the challenges out here, both eccentricity and initial geometric imperfections cause lateral displacement that appear as initial deflection in the buckling test. Okay. So, if there is an imperfection, okay, or if there is an eccentricity, okay, so both what are they going to do is that they are going to cause the lateral displacement. Okay. The effect is similar, both are trying to cause the lateral displacement. Okay. So, due to this effect, okay, due to this causality, okay, the cause is either due to the imperfections or due to the eccentricity. Okay. So, even the causes are separate, the net effect is similar. Okay. Both are causing lateral displacement, okay, and they appear as the initial deflections in the buckling test. Okay. So, that is why it becomes difficult to separate them out. Okay. In the southwell analysis, deflection caused by these two sources enter the formula similarly as the initial deflection term. Okay. When we do the southwell analysis, the deflection caused by these two sources, okay, due to these two separate causes, they are in the formula in a similar way, okay, and they are accounted as the initial deflection term. Okay. The measurement of small eccentricities and tiny imperfections precisely is challenging, okay, due to the tiny imperfections, okay, or if the eccentricity is very less. Okay. So, the measurement, the actual field measurement is very tiresome. Okay. Since the measurements are less, okay, it is very difficult to measure them precisely. Okay. Now, their combined effect is observed in the deflection data. Okay. So, whatever is the deflection data, this will be the observation due to these two separate phenomena. Okay. And when we do that, separating them out again becomes indistinguishable. Okay. To separate them out, since these things, okay, on surface are very less, okay, and their cause, okay, how they have been caused, either due to the imperfections or due to the eccentricity, okay, separating them out is a very challenging task. Okay. Also, the experimental scatter and variability add uncertainty. Okay. When we are doing an experiment, okay, we should know that there is a variability and uncertainty due to a lot of effect, due to the boundary conditions, due to the material uncertainty, okay, due to the measurement error, due to the human error. Okay. So, there is a lot of variability and uncertainty in the experiment itself. Okay. So, this adds to the complexity of measurement. Okay. So, commonly what we do is that we treat them collectively via an equivalent eccentricity. Okay. So, what we say is that whatever might be the cause, okay, we put that cause as an equivalent eccentricity, that is taking care of the deflections due to the geometric imperfections as well as deflections due to the lateral displacements. Okay. So, this is a workaround that we normally use. So, we dealt with the examples. Okay. So, in this particular example, what we did was we took out a case of static buckling. Okay. In the static buckling, okay, there was an eccentricity. So, we approximated the eccentricity via this equation, we approximated the Fourier series, we evaluated the A1 term in the Fourier series. We looked into the effect of eccentricity on the Southwell plot and effect of the eccentricity on estimation of the critical load, and then we tried to reason out why the separate effects of eccentricity and the initial imperfections are difficult to separate out during an experimental observations. Okay. So, this was a case of a static buckling case. Okay. So, now we move ahead and do the next example. Okay. So, in the next example we are dealing with the dynamic buckling, okay, and we are looking into the time evolution phenomena. Okay. So, now we have a simply supported bar. Okay. There is a simply supported bar, okay, and then suddenly applied load P is out there. Okay. The value of P is larger than the static Euler load, P is greater than PCR. Okay. We have already seen that the lateral displacement is governed by this differential equations. Okay. So, in this differential equations, okay, we derived this differential equation. First what we did was we took a simply supported bar case, okay. That bar was applied with a load P, okay, and we calculated the lateral deflection, and the lateral deflection we are measuring from the unstressed deflection. Okay. Basically, we are measuring it from the static equilibrium condition. Okay. Then what we did was we took out a chunk of this bar, okay, and this chunk of the bar we are representing out here. Okay. So, we put the resisting moment on the two faces of this differential element. We put the shear forces acting on the two faces. Okay. We marked the axial load, the effect of the axial load acting on the two faces. This is the inertia term. Okay. And after that we did the force equilibrium. So, force equilibrium in the vertical direction. Okay. We formulated this particular equation, okay, in terms of shear, and we did the moment equilibrium about point B. Okay. So, moment equilibrium about point B. So, we got the effect of the moment on the two faces. Okay. We got the effect of the axial load, okay, and we got the effect of the inertia. Okay. So, we wrote out the differential equation and we got the equation. Okay. Here we balance the moment at about point P. Okay. So, we got the equation in terms of the moment and shear. Okay. Here we ignored the effect of the rotary inertia terms and we ignored the higher order terms. Okay. And after that we use the approximation of the Euler-Bernoulli beam, okay, and using this equation we got the differential equation. Okay. So, in the differential equation, if we switch off the inertia terms, we get the equation for the static equilibrium, okay, and we solve this thing to evaluate the phenomena of the static buckling, and when we switch on this inertia term, okay, this becomes an equation for the dynamic buckling, okay, which we are again using in this particular example. Okay. So, coming back to the example, okay. So, this is the differential equation that we are using. Okay. So, here it is being asked, okay, we have a simply supported beam and a load P is being applied. Okay. So, here we are being asked to explain how the modal decomposition transformed the equation into a system of ordinary differential equations for the mode amplitude. Okay. So, we will see how it is being done. Okay. Second part is that for a given mode n, okay, describe under what condition the mode experiences exponential growth, dynamic buckling. Okay. So, and third is define the critical mode number separating stable from unstable modes. Okay. So, this thing we have already seen in the theory class. Now, we will again put this thing into practice and try to solve this equation. Okay. So, the first part, the modal decomposition and reduction to ordinary differential equations. Okay. So, first we assume the mode shapes. Okay. For a simply supported bar, the lateral displacement can be represented as the sum of the sinusoidal modes. Okay. So, basically what we are trying to do is that a system will be vibrating in a combination of all the modes. Okay. So, what we are trying to do is that we are trying to separate out each mode. Okay. So, each mode okay, each lateral displacement mode, okay, we are saying that we can represent it using a sinusoidal function. Okay. So, the lateral displacement can be represented as a sum of the sinusoidal modes. Okay. So, addition of all the modes will give me the final deflection. Okay. So, this mode shape is being approximated by a sinusoidal shape. Okay. This thing is nothing but it is giving me the different shape. As we change the n, it will give me the different shape, and this portion Qn. Okay. So, this is the shape function part, and this is the, this function will give me the magnitude, okay, magnitude of this mode. Okay. So, this is a time dependent part. Okay. So, we are separating them out into a time dependent component and a shape dependent component. Shape we are approximating using a sinusoidal function, and Qn will simply give me the amplitude. Okay. So, this way we are using the modal decomposition, okay, and we are representing the deflection, okay, in terms of a sine wave multiplied by a corresponding amplitude term. Okay. So, where Qn is the time dependent amplitude of mode n. Okay. So, Qn is nothing but the time dependent part of corresponding to the mode. Okay. And sine of this term is the spatial eigenvalue function satisfying the boundary condition that at the ends the deflection is 0. Okay. Basically, what we are trying to say is that the modes has been approximated using a sine function. Okay. This is the deflected shape, and it has been approximated using a sine function, and it obeys the boundary condition, that is the deflection at the two ends is 0. Okay. So, this is how we are approximating the lateral displacement. The same thing we have been doing earlier also. Okay. After that, we substitute this assumption, okay, or this approximation of our deflection into the partial differential equation. We substitute, say, equation number 2 into the previous equation number 1. Okay. So, when we put this thing, okay, this is how the equation will look like. Okay. So, we have substituted the part of the inertia, we have substituted the part due to the stiffness, and we have substituted the part due to the application of the lateral load. Okay. So, after that, by using orthogonality, okay, if we multiply both sides by sin pi mxn and integrate over the entire spectrum, due to the orthogonality, okay, the terms, okay, the non-orthogonal terms will go to 0. Okay. Only the term with n equals to m will survive. Okay. Only the orthogonal terms will survive. Okay. And after that, we will evaluate the spatial derivatives. Okay. Okay. And when we put this thing back into the partial differential equations, okay, using orthogonality, this will be reduced to the equation, okay, where this equation is representing the ordinary differential equations for each particular mode. Okay. So, here Qn corresponds to the particular mode, okay, the amplitude corresponding to the nth mode, amplitude corresponding to nth mode. Okay. So, that way we can write down all the equations Q1, Q2, Q3. Okay. So, here all the equations have been separated out. Okay. So, what we did was we started with the our equation, okay, the partial differential equations. Okay. From the partial differential equations, we approximated the deflection functions, okay, as a combination of the shape function and the amplitude of the shape functions for a given mode. Okay. The shape functions we are approximating using a sine function, and the time dependent part, okay, is given by n, the amplitude of the time dependent part is given by Qn. Okay. We substituted this back into the parent equation, okay, and using orthogonality, okay, we separated out the terms. Okay. So, non-orthogonal terms went to 0. Okay. So, what remained was the orthogonal terms. Okay. So, when we put this thing back into the equations, we got out ordinary differential equations, okay, for each mode. Okay. So, we are getting equations corresponding to the each mode. Okay. Omega n, okay, this term is the omega n. Okay. So, this is the effective frequency of the mode n, including the effect of the axial loads. Okay. Earlier what used to happen is that only the effect of the system comes into picture when we are evaluating the frequency. Okay. Now this is a combined frequency due to the system features as well as including the effect of the axial load. Okay. So here what we have achieved is we have transformed the partial differential equations into an infinite set of independent second order ordinary differential equations corresponding to each mode. Okay. So we took care of the first part. Okay. Second part, the condition for the exponential growth. Okay. Or the condition for the dynamic buckling. Okay. So ordinary differential equation for mode is given by these equations, where omega n, okay, omega n is been given by this part. Okay. Omega n is been given by this part. Okay. So if omega n, square of omega n is greater than 0, the solution is oscillatory. Okay. So it has a bounded mode. If omega n is, square of omega n is less than 0, the solution is exponential. Okay. It will have unbounded growth. Okay. The unstable growing part leads to the dynamic buckling in the mode A. Okay. So this unstable part will cause the dynamic buckling. Okay. Therefore the mode n buckles dynamically if omega, square of omega n value is less than 0. Okay. And after it is rearranged, we can see this will be the value, okay, which will cause dynamic buckling in the system. Okay. Okay. Moving ahead, the critical mode number separating stable and unstable modes. Okay. So we define a critical mode number NC such that omega square NC equals to 0. Okay. So in the equation for the omega n, we put a value of 0. Okay. So remember what we did first was we are evaluating, okay, based on the value of omega square. So if the value of omega square is greater than 0, the solution is oscillatory and it has bounded value. If the value of omega square is less than 0, the solution is exponential, it will cause unbounded growth. Okay. So this unstable growing part will cause the dynamic buckling in this particular mode. Okay. So there will be buckling in the mode n if the value of omega square is less than 0. Okay. So this is the criteria and this is how we evaluate the loading term. Okay. So continuing from this, okay, we are trying to establish the critical mode number, okay, that separates the stable and unstable mode. Okay. So if omega n square is greater than 0, okay, we are in this part. If omega n square is less than 0, we are in this part. Okay. So we are trying to establish this line, okay, omega n critical. Okay. So omega n critical will be evaluated at 0. Okay. So using some normalizing term, okay, we calculate the parameter, okay, critical mode number NC. Okay. So this NC is going to separate out the stable and unstable mode. Okay. So modes with n less than NC, okay, it means that omega n square is less than 0. So it will have unstable exponentially growing or buckling modes. Okay. So modes will n greater than NC, okay, meaning omega n square greater than 0, it will have stable oscillatory modes. Okay. So same thing, either we can express in terms of omega NC or we can express in terms of NC. Okay. So the dividing line is omega n square is equal to 0 or omega n equals to 0. Okay. Greater than that stable mode, less than that unstable modes. Okay. So after that we are trying to evaluate, okay, the dimensionless parameters in case of dynamic buckling. Okay. So here it is being asked to explain the physical significance of the following dimensionless parameters used in the dynamic buckling analysis. Alpha, okay, so this is the normalized axial load, eta, which is the effect of the inertia, c, the dimensionless time constant. Okay. So how does this parameter influence the evolution of the amplification of buckling mode? Okay. So what is the effect of all these parameters in the amplification of the buckling modes? Okay. So the effect of the normalized axial load, okay, the physical significance of alpha, okay, or the effect of P, okay. So alpha represents the axial compressing load, okay, normalized by the bending stiffness, okay. P is being normalized by the bending stiffness, okay, and appropriately the terms have been adjusted so that the alpha becomes dimensionless. Okay. So, it is a measure of how large the applied load is relative to the stiffness and geometry of the bar. Okay. P is the applied load in the system, okay, and EIL square is the measure of the bending stiffness of the system. Okay. So, the applied load is measured with respect to the stiffness of the system. Okay. What is its role in buckling? So, the higher value of alpha corresponds to the higher compressive load. Okay. If alpha is higher, it means that P is higher, okay, and it means that the compressive loading is higher and it will promote the buckling instability. So, it is going to cause buckling instability. Alpha directly affects the static buckling condition. Okay. The classical Euler critical load corresponds to a critical value of alpha equals to pi square for the lowest buckling mode n equals to 1. Okay. In case of dynamic buckling, the dynamic buckling can occur for alpha beyond this critical value. Okay. After this critical value, the dynamic buckling might occur, okay, with increasing alpha causing more modes to become unstable. Okay. So, as alpha increases, more and more modes will become unstable and it will grow exponentially. Why? We can see this thing in case of the equation also. Okay. Here what we are saying is that as P increases, okay, this term, the omega square, okay, will become less than 0. So, as we increase the value of P, omega n will become less than 0, okay, and it will force the system into more and more modes into the unstable equilibrium. Okay. Influence. So, alpha controls the range of unstable modes. Okay. Higher the value of alpha, higher the value of P, and it is more likely that more number of omegas are unstable. Okay. So, as alpha increases, the critical mode number NC increases, causing more modes to become buckling modes that grow exponentially in time. Okay. Simply by looking in this equation, we can have this inference. P increases, more number of omega n becomes less than 0. It means that more and more modes are forced into the unstable buckling modes. Okay. The effect of the inertia, physical significance. So, eta quantifies the relative importance of the initial forces. Okay. That is the mass. This term is the mass with respect to the elastic bending stiffness. Okay. Again, it has been normalized with respect to the bending stiffness of the system. So, role in buckling, it appears in the dynamic equation of motion as the coefficient of the inertial terms. Okay. So, this thing is appearing as the coefficient of the inertial terms. Okay. So, it is appearing here. Okay. Okay. So, large eta means that inertia effects are more significant and influence the time response and stability. Okay. So, the effect of the inertia, it governs the natural elastic vibration frequency of the bar without the axial load. Okay. So, as we have seen earlier, okay, so this term, okay, in the absence of the axial loading, okay, this will be related with the frequency. Okay. So, it will govern the frequency. Okay. So, frequency without the axial term will be given by this part, and here the frequency is influenced by the inertia term. Okay. After that, it affects the dynamic behavior of the system with inertia resisting sudden large acceleration. Okay. So, inertia is trying to cause the resistance in the system, and coupled with the axial load effect, it determines the critical condition and rate of growth of the unstable mode. Okay. So, this is present in the equation of omega square, okay, and combined with the relative value, okay, of this two, okay, it will determine whether omega n is going into the unstable oscillatory mode or in a stable mode. Okay. The effect of the dimensionless time. Okay. So, what tau is doing is that it normalizes the physical time by the time travel of the elastic wave over the bar length. Okay. So, what it is being done is that it is being normalized with respect to the axial wave speed. Okay. So, it is a scale time variable used for describing how quickly the dynamic buckling evolves relative to the speed of the stress waves in the bar. Okay. The role in buckling mode amplitude grows over time depending upon the value of tau. It characterizes a temporal evolution of instability, allowing amplification functions, growth of buckling amplitude relative to the initial imperfections to be expressed in a universal scaled form, independent of the actual LNC. Okay. So, it gives an independent expressions growth of the buckling amplitudes. Okay. So, what it is influencing? The buckling amplification increases sharply after a critical dimensionless time tau c. Okay. We have seen that after a time tau c, if it is greater than 5, the buckling amplitude increases sharply. Okay. Where the exponential growth of the mode amplitude dominates the space and time continuum. So, what it does is that it facilitates the prediction of the maximum safe load duration before buckling can reach an unacceptable limit. Okay. So, basically it will tell you how long, okay, the system has before it buckles and it reaches an unacceptable amplitude. Okay. So, with this we come to an end of the chapter. Please do the examples. Okay. Good luck.